Hi all, welcome to the channel. So today we'll be looking at day 20 of the October LeetCode challenge. The name of the problem is clone graph. Let's look into the problem. So the problem states, given a reference of a node in a connected undirected graph, return a deep copy of the graph, which is clone of the graph. So each node in the graph contains a value, which is an int value, and a list, which is a list of nodes of its neighbors. So this is the structure of the class for the node, and it has a value and the list of neighbors. So the test case format is, for simplicity's sake, each node's value is the same as the node's index. So it starts with one index. For example, the first node with val equal to 1, the second node with val equal to 2, and so on. The graph is represented in the test case using an adjacency list. Adjacency list is a collection of unordered lists used to represent a finite graph. Each list describes a set of neighbors of a node in the graph. The given node will always be the first node with a value equal to 1. You must return the copy of the given node as a reference to the clone graph. So when it says you have to return a copy, that means it should not be the same reference as the node that has been provided. You have to create a new reference. So that's what they have shown here. So if the original graph is 1, 2, 3, 4, here when they say that you cannot return the same graph, that means that the reference should not be same of the original graph. You have to create a new node for each of the nodes in the graph. So here there are new nodes, and when you create new nodes for each of the nodes in the graph, it is called the clone of the graph, and that you have to return back. And also, even if you create a clone, but if the order of the elements, that is the order of the nodes, are not correct, even in that case it's not a correct result. So you have to make sure that the order of elements are also correct. That means here the neighbor of 1 is 2 and 4, so you cannot have a neighbor of 1 as 3 and 4. It has to be 2 and 4. Okay, so let's look into the example here. So here the adjacency list is 2 4 1 3 2 4 1 3. So what this means is, for the index 1, right, so here the node is 1, for that one the adjacency list is 2 and 4. Okay, so that's what they have provided here. Similarly, for the index 2, the adjacency list is 1 and 3, so that's what it's given here. Then after 2 there is 3, so for 3 it's 2 and 4 as the neighbors, so 2 and 4, and for 4 1 and 3 again is the neighbor. So you have to return the same list but with new nodes. Okay, so the reference should not be same. Similarly, in this case, if it is empty, so that means for this one node there is no neighbors, right? So it is empty, so you have to return it same way. And if the whole list is empty, that means there is no node at all. In that case also you have to return empty list or empty graph. Okay, in this example, for 1 the neighbor is 2, and for 2 the neighbor is 1. So here they have shown that for the first index the neighbor is 2, for the second index the neighbor is 1. So you have to return it that way. The node.val will be between 1 and 100. So that is a constraint, and node.val is unique for each node. Number of nodes will not exceed 100 because node.val is unique for each node, and node.val is between 1 and 100. So obviously number of nodes will be less than or equal to 100. There is no repeated edges and no self loops in the graph. The graph is connected and all nodes can be visited starting from the given node. So they have said that there is no self loop, so we don't have to check for the self loop here. So what we can do here is we have to create nodes for each of the nodes that we have in this, right? So we have to create a new node for this particular current node that we have, and then we have to find out the neighbors of this node and create a new node for the same neighbors as well, right? So the first thing is, if I go back to that example 2 and 3, I think, yeah, here, right, if the graph is empty we can return directly the empty, that is null. And if it is here also, if it is empty, then also we can return empty, right? This will be empty list, right? So let's take care of that first. If node is null, I can directly return null. So if node is null, then I can directly return null. Now else I need to create a node 1. So I am creating a copy of this node with the same value. So this is node 1, and once I create the copy I can go over the neighbors of the node. node n in node dot neig. So for each neighbor I need to again create a new node, right, for that neighbor. So basically that is same as calling this function, right, because this function was also doing the same thing, right. So we can recursively call this function. So here we can do that. This is a node, so I can say that node 1 dot neighbors dot add, because neighbors is a array list, right. So we created a new node 1 and currently we created with the node dot val, but this node 1 is not having any neighbors currently, right. We have to copy the neighbors of this node into this node 1, right. So that's what we are doing here. We are iterating over the neighbors of node and we are copying it into node 1. So we are adding it into node 1's neighbor. While doing that we are doing node 1 dot add and I am again calling the clone graph function to add the neighbor. So this will be n, and at the end I can return my new node 1. Okay. Now if you see, if I add this way, right, let's see what will happen, right. So this is the case, right, 1 2 3 4, right. So first node is 1, for 1 the neighbors are 2 and 4, then it will go to 2, for 2 the neighbor is 1 and 3, right. So if you see, it will again go to 1 and again for 1 it will go to 2 and 4. So this will go in a recursive operation which will be infinite, right. So to break that, what we can do is, if one is already created, right, we don't need to again call the clone graph method, right, recursively. We have to stop that recursive operation. So there should be some way to track whether the node is created or not, right. So for that what we can do is, since it's given that the values will be unique, right, we can create a hash map and store the key as the integer and value as the node value. So let's do that. So I'll create a map with key as the integer and value as the node. Map equal to new hash map. Now here you can also use the key as the node, but that is not recommended. The reason is because in this particular case I tried with both node and integer and that works fine, but in a real life scenario you should not do that unless you cannot override the node function with your hash code, unless you know that the hash code implementation is not giving you any collision. You should not go for that. So since I cannot override the hash code, it's recommended that I should go with the integer, because I know the integer value, which is the value of the node, will be unique. So I should go with that as the key value. So here I am using integer and node. So what I can do is, once the new node is created, I can add that new node value into my map. So map dot put node dot val comma node 1. So this way I am storing the node dot val and node 1, which is the reference to the new node that I created, right. Now here when I call this recursively, right, at that time, before doing all this operation, right, that means before creating the new node, I can check here if my map already contains that. So let me add that condition here. If map dot contains key node dot val, if my map already has that, in that case then directly return that node. Okay. So this way it won't create a new node or it won't recursively call the clone graph, right. We are passing the same reference of the node that we created. Okay. So if there are 4 objects or 4 nodes, it will only create 4 nodes and it will pass the reference of that 4 node to be added as neighbors in the all other nodes. Okay. So let's submit this code and see whether it works fine. So the test case executed properly. Let's submit this and the code is accepted. So the runtime of this algorithm will be O of n, because we are doing a DFS and it has to go through each and every node. So n is the number of nodes, so it will be O of n, and the space complexity will be again O of n, because we are creating a hash map to store the nodes into the map as well. So space complexity is also O of n. So hope you like the solution. please do hit the like button and do subscribe to the channel if you haven't already. Thank you.